We are still talking about forces, and in this lesson, which is lesson 13, we're going to be talking about um force diagrams and free body diagrams. So if you've written a physics paper, you know normally there will be a question asking you to draw maybe a situation, a free body diagram of of a certain situation. So at least at the end of this lesson, you should be able to draw force and free body diagrams of different scenarios and actually differentiate between what is a free body diagram and what is a force diagram. So let us do that. It's not going to be a hectic lesson. We're just going to be drawing the force diagrams and free body diagrams for different scenarios. So, what are force diagrams? Force diagrams are sketches of the physical situation that you're dealing with. And then you would actually show arrows for all the forces that are acting on a system. So, if you have a car, you would actually draw a, a car, and then you will draw all the forces that are acting on that car, if those were the forces. So it's just the physical situation that you're dealing with. So let's take for an example, if you have a block of a wooden block, it can be any type of a block, and it's resting on a horizontal surface or on a table. So you would draw your table. These are the legs of the table, and then you would draw your block there. It's on top, right? And then you would say, okay, let's say there was no applied force and there was also no friction. So the only forces acting on this would be your perpendicular force, which is your normal force. So remember Fn, which is your normal. It's not equals to, but this is just the normal. And then from the center of this block, you'd also have Fg. So remember Fn, okay, is your normal, and then Fg is your gravity. So that's how you would draw the situation. So we've drawn the block. So we've actually drawn the physical situation that we're dealing with. But now, for example, let's say the same block is still on a table, but now there's now an applied force. Maybe it's accelerating in a certain direction, and you are asked to draw. I'm sorry for that. You're asked to draw the force diagram for that. So let's say you have an applied force. It's moving to the right. So you have F applied. And then you have friction. Maybe it's a rough surface. And then you'll have FR. So that's your friction. And then you still have that perpendicular force that is exerted by the surface on an object in contact with it, and we call that the normal, right? And then from the center of that, you can draw your Fg, which is your gravity. So this is just a basic example. And then now we actually now going to be talking about free body diagrams and what is the difference between the two. So in a free body diagram, the object of interest is drawn as a dot, and all the forces acting on this object are drawn as arrows, and they're all pointing away from the dot. That is an important thing. All of them are pointing away from the dot. So now let us draw free body diagrams of these situations. But before we do that, I want you to keep in mind, so the length of an arrow, if say we say this is Fn, and then Fg is just pointing downward, which is gravity. So if you look at these arrows are the same length. If I'm a marker, I would assume that you're saying that the normal force is equal to Fg. If they were not equal, and let's say Fg was larger, so gravity was larger, say Fn, you'd actually have to draw a gravity, show gravity with a longer arrow to indicate that no, in this situation my gravity is actually larger than so the length of an arrow actually indicates the magnitude or the size of the force that you're talking about. So now, like I mentioned, let us draw free body diagrams for this situation. So the object, the block, would be represented by a dot, as they've mentioned. Can do the same on this side as well. and then we would have an arrow pointing away from the dot for the normal force, an arrow pointing away from the dot, which is Fg. So these two are actually supposed to be equal. Fg is supposed to be equal to Fn. Just that, so when you draw this, you're gonna use a ruler, of course. And then this situation over here, we have an arrow which indicates our object of interest, and then we have the normal force Fn, we have gravity Fg, and then we have the applied force Fa, and then we have friction Fr. So that's how you would draw this free body diagram for this situation. So another thing before we move on that I would like to mention is that if you're going to just be writing Fn, Fr, or Fa, it's important that in a table, or it doesn't even have to be table, just describe what is Fn. So you'd say, okay, this is normal force. So you have to indicate what each force is. So as I've done here, so you'll tell me that Fn is normal force, Fg is gravity, Fr is friction, and Fa is applied force. Otherwise, I'm not sure. Imagine if I'm not a person with a physics background. How do I know what Fn and Fa and all of these things are? So do not make that mistake. Always make sure that you include this, just to be on the safe side, and not just assume that the examiner is going to know what Fa or F what is, because people use different notations. Some person might write F friction as FF. So they have to explain to us what FF is. Or yeah, so now let us move on and draw more free body diagrams for different situations. So my focus is mainly going to be on free body diagrams, because that is what you normally asked to draw in an exam. Okay, so let's say you have now a block that is pulled at an angle theta. I'm not write that there. So you have this block here, and there's a pulling force that is applied to it at a certain angle. So it makes that theta, or with the angle theta with the horizontal. And now you are asked perhaps to draw a free body diagram of this situation. So you have your gravity there, you have your frictional force. Remember, friction is always opposing motion. So this block is actually moving in this direction, and then you have your normal and everything else. So you represent the block with a dot, and then you would draw your normal force, and then maybe your Fg, and then you would draw this angle, this applied force here, and then you would have your frictional force. And remember to always describe somewhere that Fn is normal, Fr is friction, Fa is applied force, and Fg is your gravity. So now let us consider a different situation. So in this situation, we have a block being pushed at an angle. So it's actually moving in this direction. And friction, if it's moving in this direction, meaning friction will pull at the other direction, and then your normal and your gravity. So let's draw a free body diagram for this situation. You would draw your normal, your gravity, and then you will also draw that force there. Remember that in a free body diagram, all the forces have to be moving away from the dot. So Fa would actually be drawn here, and then you have your frictional forces. So that is just how you would draw this. And remember, we're just talking about objects on a horizontal surface. We haven't talked about objects on a slope, and we're going to be talking about them next. So now let us consider a situation such as this one. This is really not clear here. So this is Fg parallel. Yeah. Okay, so now we have an object on a slope, and then this object is actually being pushed downwards. So it's moving downwards. So the F applied is down the slope. And then of course we have the force of gravity, and we have now resolved the force of gravity. We've spoken about how to do this into its perpendicular. So maybe here you have theta. It's a very small sketch I'll make it bigger next time, and then you can resolve this into its x and y component. And then you have frictional force, which is always opposes motion. So how do you draw a free body diagram for that situation? So you would say, okay, there are two ways. You can say, okay, I'll draw it when in a situation where I don't include the components. So you have your normal force, then you have your gravity, and then you have your frictional forces, Fr, and then Fa. Or someone might say, if you decide to include the components, you actually do not include the force. So if you include in the force the components of Fg, you don't draw the thingy, the arrow for, okay, I'm not sure why I'm making it a dotted line, Fg parallel. So you only draw Fn. Let me finish this so that I can, then we have Fr, and then we also have Fa here, applied force. So let's say it's Fa. I know it looks terrible, but yeah, that's basically how you draw it. So if you decide to draw it this way, where you want to include the components, you actually do not draw the actual force vector. But if you draw the actual force vector, you don't include the components. So that is just something to be mindful of when drawing diagrams in this situation over here. Let us consider a different situation. Okay, so now let us say you have your force applied this up the slope. So your object is moving upwards. So you have your normal, your gravity, your applied force, and then friction always opposes motion. So it's going to be faced that way. And now we have resolved this gravity vector into its parallel and perpendicular component. So this is its perpendicular component, Fg perpendicular, and this is its parallel component. So now let's draw a free body diagram for that situation. So like I mentioned, there are two ways. You can say, okay, I don't want to include the components. If you don't include the components, you have to include the force, Fg, and then we have Fn, which is your normal force, and then we will have applied force, which is up the slope, and now frictional force, which is down the slope. All right. But now if you decide that I want to include my components, that means that you actually don't include this first vector, you just include in the components. So you would include your Fg perpendicular, your Fg parallel, which is down the slope, and then also down the slope, remember we have Fr, and then you would have your Fn, which is your normal, and then finally your F applied, which is your force applied, and it's up the slope. Another situation, the last situation we can consider, but there are many different situations. You just have to really look what it is that you're given. Are you given the friction? Do they say it's frictionless? If they say it's frictionless, then you don't include friction and everything. So now let's just consider objects that are hanging. If you have an object that is hanging over a wire or something, or a rope, in that case you would draw, this is your object, and then you would have a tension, Ft, and then you would have gravity, which is Fg. But then if your object is in free fall, so it's only moving under the influence of gravity, so it's just going down. The only force that is acting on it is gravity. And how you draw that free body diagram is this way. So like I mentioned, there are many other ways. The trick is to look at these previous question papers and see what is it that they ask. Also look at the number of marks. If the number of marks for that is like 5 marks and they asked you to draw a free body diagrams, it should kind of intuitively tell you that they are requiring you to probably show 5 forces at most. So that is always your guide. So also know the difference between angle forces that for force diagrams for things that are moving up a slope, and when something is actually on a horizontal surface, so it's not on a slope, but we have a force that is acting on it at a diagonal direction. And I think this brings us to the end of this lesson.